643 space facts to fall asleep to. Welcome to this journey through the cosmos. Get comfortable, relax, and let these fascinating facts about space gently guide you into peaceful sleep. Our universe began approximately 13.8 billion years ago in an event we call the Big Bang. In the first fraction of a second, all the matter and energy that would ever exist came into being. The observable universe is about 93 billion light-years in diameter. This means light from the edge of what we can see has been traveling toward us since nearly the beginning of time itself. There are estimated to be 2 trillion galaxies in the observable universe. Each one contains millions, billions, or even trillions of stars. Our own galaxy, the Milky Way, contains between 100 and 400 billion stars. We're still not entirely sure of the exact number. The Milky Way is about 100,000 light-years across. If you could travel at the speed of light, it would take you 100,000 years to cross from one side to the other. Our solar system is located about 26,000 light-years from the center of the Milky Way. We orbit around the galactic center once every 230 million years. The last time Earth was in this position in the galaxy, dinosaurs were just beginning to appear on our planet. The Milky Way and the Andromeda Galaxy are moving toward each other at about 250,000 miles per hour. They will collide in about 4 billion years. When galaxies collide, the stars within them rarely actually hit each other. The distances between stars are so vast that they mostly pass through each other like ghosts. The Sun contains 99.86% of all the mass in our solar system. Everything else, all the planets, moons, asteroids, and comets, make up just 0.14%. The Sun is about 4.6 billion years old. It's roughly halfway through its life cycle. Every second, the Sun converts about 600 million tons of hydrogen into helium through nuclear fusion. This process releases an enormous amount of energy. The Sun's core temperature is about 15 million degrees Celsius. The pressure there is so intense that hydrogen atoms are forced together to create helium. Light from the Sun takes about 8 minutes and 20 seconds to reach Earth. This means we always see the Sun as it was 8 minutes ago. The Sun's light takes only 8 minutes to reach us, but the energy produced in the core can take between 10,000 and 170,000 years to reach the surface. The Sun loses about 4 million tons of mass every second through the energy it radiates. Despite this, it's so massive that it will continue shining for another 5 billion years. In about 5 billion years, the Sun will expand into a red giant. It will grow so large that it will likely engulf Mercury, Venus, and possibly Earth. After the red giant phase, the Sun will shed its outer layers and become a white dwarf. It will slowly cool over trillions of years. The Sun rotates on its axis, but because it's made of gas, different parts rotate at different speeds. The equator completes a rotation every 25 days, while the poles take about 36 days. The Sun's magnetic field flips approximately every 11 years. This cycle is connected to sunspot activity. Sunspots are temporary dark spots on the Sun's surface. They're caused by magnetic activity and are actually cooler than the surrounding areas, though still incredibly hot at about 3,500 degrees Celsius. Solar flares are massive explosions on the Sun's surface. The largest ones release as much energy as 1 billion hydrogen bombs. The Sun produces a stream of charged particles called the solar wind. This wind flows out into space in all directions at speeds of about 1 million miles per hour. When the solar wind interacts with Earth's magnetic field, it can create auroras near the poles. These beautiful light displays are called the northern and southern lights. The Sun makes up about 99.8% of the mass of our entire solar system. Jupiter contains most of the remaining mass. Mercury is the smallest planet in our solar system and the closest to the Sun. It's only slightly larger than Earth's moon. Mercury has almost no atmosphere. Without air to trap heat, temperatures can range from 430 degrees Celsius during the day to minus 180 degrees Celsius at night. A day on Mercury from sunrise to sunrise lasts 176 Earth days. Interestingly, a year on Mercury is only 88 Earth days. Mercury has a huge iron core that makes up about 75% of the planet's radius. This gives it the second highest density of any planet in the solar system after Earth. Venus is often called Earth's sister planet because they're similar in size and mass. However, the similarities end there. Venus has the hottest surface of any planet in our solar system, with an average temperature of 464 degrees Celsius. This is hot enough to melt lead. The thick atmosphere of Venus is made mostly of carbon dioxide with clouds of sulfuric acid. The atmospheric pressure at the surface is 92 times greater than Earth's. Venus rotates in the opposite direction to most planets in our solar system. If you could stand on Venus, you would see the sun rise in the west and set in the east. A day on Venus, one full rotation, takes 243 Earth days. A year on Venus is only 225 Earth days. This means a day on Venus is longer than its year. Venus has no moons and no rings. It's one of only 2 planets in our solar system without any moons, the other being Mercury. Earth is the only known planet with liquid water on its surface. Water covers about 71% of our planet's surface. Earth's atmosphere is about 78% nitrogen and 21% oxygen. This unique combination is essential for life as we know it. Our planet has one natural satellite, the Moon. The Moon is gradually moving away from Earth at a rate of about 3.8 centimeters per year. Earth's magnetic field protects us from harmful solar radiation. Without it, life as we know it would not be possible on the surface. The Moon was likely formed about 4.5 billion years ago when a Mars-sized object collided with Earth. The debris from this impact eventually coalesced to form the Moon. The Moon is tidally locked to Earth, meaning the same side always faces us. We never see the far side of the Moon from Earth without spacecraft. The Moon's gravity causes tides in Earth's oceans. There are typically 2 high tides and 2 low tides each day. The Moon has no atmosphere, no weather, and no sound. Footprints left by astronauts will remain there for millions of years. During a total solar eclipse, the Moon perfectly covers the Sun from our perspective. This is a cosmic coincidence because the Sun is about 400 times larger than the Moon, but also 400 times farther away. The Moon's surface is covered in craters from billions of years of asteroid and comet impacts. Without an atmosphere to protect it, every impact leaves a permanent scar. The temperature on the Moon can vary from 127 degrees Celsius in direct sunlight to minus 173 degrees Celsius in shadow. Mars is often called the red planet because of iron oxide or rust on its surface, giving it a reddish appearance. Mars has the largest volcano in the solar system. Olympus Mons is about 25 kilometers high, nearly 3 times the height of Mount Everest. Mars also has the largest canyon in the solar system. Valles Marineris is about 4,000 kilometers long and 7 kilometers deep in places. A day on Mars is very similar to Earth's, lasting 24 hours and 37 minutes. However, a year on Mars is 687 Earth days. Mars has 2 small moons named Phobos and Deimos. They're irregularly shaped and are probably captured asteroids. Phobos is gradually spiraling inward and will either crash into Mars or break apart to form a ring around the planet in about 50 million years. Mars once had liquid water on its surface. Ancient river valleys and lake beds provide evidence of a wetter past. The atmosphere on Mars is very thin, about 1% the density of Earth's atmosphere. It's mostly carbon dioxide. Dust storms on Mars can cover the entire planet and last for months. These storms can reach wind speeds of up to 100 kilometers per hour. The highest recorded temperature on Mars is about 20 degrees Celsius near the equator during summer. The average temperature is about minus 63 degrees Celsius. Between Mars and Jupiter lies the asteroid belt, a region containing millions of rocky objects. These are remnants from the early solar system that never formed into a planet. The largest object in the asteroid belt is Ceres, a dwarf planet about 950 kilometers in diameter. It contains about a third of the total mass of the asteroid belt. Jupiter is the largest planet in our solar system. It's so large that all the other planets could fit inside it. Jupiter is a gas giant made mostly of hydrogen and helium. It has no solid surface that we know of. The Great Red Spot on Jupiter is a massive storm that has been raging for at least 300 years. It's so large that 2 or 3 Earths could fit inside it. Jupiter rotates faster than any other planet in our solar system. A day on Jupiter lasts only about 10 hours. Jupiter has at least 95 known moons. The 4 largest, called the Galilean moons, are Io, Europa, Ganymede, and Callisto. Europa, one of Jupiter's moons, has a surface covered in ice. Beneath this ice is believed to be an ocean of liquid water that might harbor life. Ganymede is the largest moon in our solar system. It's even larger than the planet Mercury. Io is the most volcanically active body in the solar system. Its surface is constantly being reshaped by volcanic eruptions. Jupiter has a faint ring system, though it's nowhere near as spectacular as Saturn's rings. These rings are made of dust particles kicked up by impacts on Jupiter's small inner moons. Jupiter's magnetic field is 14 times stronger than Earth's. It creates intense radiation belts around the planet. Saturn is the second largest planet in our solar system and is famous for its spectacular ring system. Saturn's rings are made mostly of ice particles, with some rock and dust mixed in. The particles range in size from tiny grains to house-sized chunks. Saturn's rings are surprisingly thin. While they stretch hundreds of thousands of kilometers across, they're typically only about 10 to 100 meters thick. Saturn has at least 146 known moons. The largest, Titan, is bigger than the planet Mercury. Titan is the only moon in our solar system with a thick atmosphere. Its atmosphere is even denser than Earth's. Lakes and seas of liquid methane and ethane exist on Titan's surface. It's the only other body in our solar system besides Earth known to have stable liquid on its surface. Saturn is the least dense planet in our solar system. It's so light that it would float in water if you could find a bathtub large enough. A day on Saturn lasts about 10 hours and 33 minutes. A year on Saturn is about 29 Earth years. The winds on Saturn can reach speeds of up to 1,800 kilometers per hour. These are some of the fastest winds in the solar system. Saturn has a hexagonal storm at its north pole. Each side of this hexagon is wider than Earth, and the storm has been raging for decades. Uranus is an ice giant, the 3rd largest planet in our solar system. It's made mostly of water, methane, and ammonia ices surrounding a rocky core. Uranus rotates on its side. Its axis of rotation is tilted 98 degrees, meaning it essentially rolls around the sun like a ball. Because of its extreme tilt, each pole of Uranus experiences 42 years of continuous sunlight, followed by 42 years of darkness. Uranus has a blue-green color due to methane in its atmosphere. Methane absorbs red light and reflects blue and green light. Uranus has 13 known rings, though they're much fainter than Saturn's. These rings are made of dark particles. Uranus has at least 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. A day on Uranus lasts about 17 hours. A year on Uranus is about 84 Earth years. Uranus was the first planet discovered with a telescope. It was found by William Herschel in 1781. The temperature in Uranus's upper atmosphere is about -224 degrees Celsius, making it the coldest planetary atmosphere in the solar system. Neptune is the 8th and farthest planet from the Sun in our solar system. It's another ice giant similar to Uranus. Neptune has the strongest winds of any planet in our solar system, reaching speeds of up to 2,000 kilometers per hour. Neptune appears blue because of methane in its atmosphere, similar to Uranus, but Neptune's blue is more vivid. Neptune has 14 known moons. The largest, Triton, is geologically active and has geysers that erupt nitrogen gas. Triton orbits Neptune in the opposite direction to the planet's rotation. This suggests it was captured by Neptune's gravity rather than forming alongside the planet. Triton is slowly spiraling inward toward Neptune. In about 3.6 billion years, it will either crash into Neptune or break apart to form a ring system. Neptune has 6 known rings, though they're very faint and difficult to observe from Earth. A day on Neptune lasts about 16 hours. A year on Neptune is about 165 Earth years. Neptune was discovered in 1846 through mathematical predictions before it was observed telescopically. Irregularities in Uranus's orbit led astronomers to predict another planet's existence. The Great Dark Spot was a massive storm on Neptune similar to Jupiter's Great Red Spot. It was observed by Voyager 2 in 1989 but had disappeared by 1994. Beyond Neptune lies the Kuiper Belt, a region of icy bodies similar to the asteroid belt but much larger and more distant. Pluto is the most famous object in the Kuiper Belt. It was considered the ninth planet from its discovery in 1930 until 2006, when it was reclassified as a dwarf planet. Pluto has 5 known moons. The largest, Charon, is so large relative to Pluto that they're sometimes considered a double dwarf planet system. Pluto's surface has plains of frozen nitrogen, mountains of water ice, and a heart-shaped region called Tombal Regio. Pluto's atmosphere is very thin and consists mainly of nitrogen with some methane and carbon monoxide. When Pluto is farthest from the Sun, the atmosphere freezes and falls to the surface. A day on Pluto lasts about 6.4 Earth days. A year on Pluto is about 248 Earth years. Pluto's orbit is highly elliptical. Sometimes it's closer to the Sun than Neptune, though the two will never collide due to the way their orbits are aligned. Pluto was named by an 11-year-old girl named Venetia Burney. She suggested the name of the Roman god of the underworld. The New Horizons spacecraft flew by Pluto in July 2015, giving us our first close-up views of this distant world. Beyond the Kuiper Belt lies the Oort cloud, a theoretical spherical shell of icy objects surrounding our solar system. It may extend halfway to the nearest star. Comets are icy bodies that develop tails when they approach the Sun. The heat causes ice to sublimate, creating a glowing coma and tail. Comet tails always point away from the Sun, pushed by solar wind and radiation pressure. This means a comet's tail actually leads the way as it moves away from the Sun. Halley's Comet returns to the inner solar system every 75 to 76 years. It will next be visible from Earth in 2061. Some comets have been visiting the inner solar system for thousands of years, while others are making their first trip from the Oort cloud. When a comet's orbit brings it close to the Sun regularly, it gradually loses its ice and can eventually become extinct, leaving behind only a rocky core. Meteor showers occur when Earth passes through debris left behind by comets. The particles burn up in our atmosphere, creating streaks of light. A shooting star is not a star at all, but a small piece of space debris burning up in Earth's atmosphere. Most are no larger than a grain of sand. Larger pieces of space debris that survive the journey through the atmosphere and hit the ground are called meteorites. The largest meteorite ever found on Earth is the Hoba meteorite in Namibia. It weighs about 60 metric tons. About 48 tons of meteoritic material falls to Earth each day, though most of it is in the form of tiny particles. The dinosaurs were likely wiped out by a massive asteroid impact 66 million years ago. The impact crater, called Chicxulub, is located on Mexico's Yucatan Peninsula. The asteroid that killed the dinosaurs was probably about 10 kilometers in diameter. The impact released energy equivalent to billions of nuclear bombs. Earth is hit by a car-sized asteroid about once a year. These usually burn up in the atmosphere before reaching the ground. An asteroid about the size of a football field hits Earth roughly every 2,000 years. These can cause significant regional damage. Asteroids large enough to cause global catastrophe, like the one that killed the dinosaurs, hit Earth roughly every 100 million years. NASA and other space agencies actively track potentially hazardous asteroids. There are currently no known asteroids on a collision course with Earth. The nearest star to our Sun is Proxima Centauri. It's about 4.2 light-years away. If you could travel at the speed of the fastest spacecraft humans have ever built, it would take about 70,000 years to reach Proxima Centauri. Proxima Centauri is a red dwarf star much smaller and cooler than our Sun. It has at least 2 known planets. One of Proxima Centauri's planets, Proxima Centauri b, orbits in the star's habitable zone, where liquid water could exist on its surface. Red dwarf stars are the most common type of star in the galaxy. They're small, cool, and can burn for trillions of years. Our Sun is a yellow dwarf star, which is actually medium-sized. It's larger and hotter than red dwarfs, but smaller and cooler than giant stars. The brightest star in Earth's night sky is Sirius. It's actually a binary star system with a bright main star and a faint white dwarf companion. Betelgeuse is a red supergiant star in the constellation Orion. It's so large that if it replaced our Sun, its surface would extend past the orbit of Mars. Betelgeuse is expected to explode as a supernova sometime in the next 100,000 years. When it does, it will be visible during the day on Earth. When a massive star runs out of fuel, it explodes in a supernova. This explosion can briefly outshine an entire galaxy. Supernovae are responsible for creating and dispersing heavy elements throughout the universe. Every atom of gold, silver, and uranium in existence was created in a supernova. After a supernova, if the remaining core is massive enough, it can collapse into a black hole. If it's less massive, it becomes a neutron star. Neutron stars are incredibly dense. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. Neutron stars can spin hundreds of times per second. These rapidly rotating neutron stars are called pulsars because they emit beams of radiation that sweep past Earth like a lighthouse. The fastest spinning pulsar known rotates 716 times per second. This is faster than a kitchen blender. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. The event horizon is the point of no return around a black hole. Once anything crosses this boundary, it cannot escape. At the center of a black hole is a singularity, a point where density becomes infinite and our understanding of physics breaks down. Time behaves strangely near black holes. If you could watch someone fall into a black hole, you would see them slow down and freeze at the event horizon, though they would feel themselves falling normally. Black holes don't actually suck in material like a vacuum cleaner. If the Sun were suddenly replaced by a black hole of the same mass, Earth would continue orbiting normally. There's a supermassive black hole at the center of most galaxies, including our Milky Way. Our galaxy's black hole is called Sagittarius A star. Sagittarius A star has a mass of about 4 million times that of our Sun. Despite this, it's relatively quiet compared to black holes in other galaxies. The first image of a black hole was captured in 2019. It showed the supermassive black hole at the center of the galaxy M87. The M87 black hole has a mass of about 6.5 billion times that of our Sun. It's incredibly far away, about 55 million light-years from Earth. When matter falls into a black hole, it forms an accretion disk that can heat up to millions of degrees and emit powerful radiation. Some black holes produce jets of material that shoot out at nearly the speed of light. These jets can extend for thousands of light years. Stellar mass black holes form from the collapse of massive stars. They typically have masses between about 3 and several dozen times the mass of the Sun. Supermassive black holes can have masses of millions or billions of times the mass of the Sun. Scientists are still trying to understand how these giants formed. There may also be intermediate mass black holes with masses between stellar and supermassive black holes, but they're harder to detect and less common. Primordial black holes are theoretical black holes that could have formed shortly after the Big Bang. They could have any mass, even as small as an atom. Some scientists think primordial black holes could make up some or all of dark matter, though this is still speculative. If two black holes orbit each other, they produce gravitational waves, ripples in the fabric of space-time itself. Gravitational waves were first directly detected in 2015. The signal came from two black holes merging about 1.3 billion light-years away. When those two black holes merged, they converted 3 times the mass of the Sun into pure energy in the form of gravitational waves in just a fraction of a second. Einstein predicted gravitational waves in 1916, but it took a century for technology to advance enough to detect them. Gravitational waves travel at the speed of light. They slightly stretch and squeeze space as they pass through, but the effect is incredibly tiny. The detectors that discovered gravitational waves, called LIGO, can measure distortions in space smaller than 1/10,000th the diameter of a proton. Binary star systems are very common. More than half of all stars exist in systems with 2 or more stars. In a binary system, the stars orbit around their common center of mass. Sometimes one star can steal material from its companion. Some binary systems have stars so close together that they touch, sharing their outer atmospheres in what's called a contact binary. If one star in a binary system becomes a white dwarf and pulls material from its companion, the stolen material can pile up on the white dwarf's surface and periodically explode in what's called a nova. If enough material accumulates on a white dwarf, it can trigger a runaway nuclear reaction that completely destroys the star in a Type 1a supernova. Type Ia supernovae are important to astronomers because they always explode with the same brightness, making them useful for measuring cosmic distances. White dwarfs are the remnants of stars like our Sun after they've shed their outer layers. They're about the size of Earth, but contain as much mass as the Sun. White dwarfs are held up against gravity, not by nuclear fusion, but by electron degeneracy pressure, a quantum mechanical effect. White dwarfs gradually cool over billions of years, eventually becoming black dwarfs. However, the universe isn't old enough yet for any black dwarfs to exist. The Chandrasekhar limit is the maximum mass a white dwarf can have, about 1.4 times the mass of the Sun. Above this mass, the white dwarf will collapse. Brown dwarfs are objects too massive to be planets, but not massive enough to sustain hydrogen fusion like stars. They're sometimes called failed stars. Brown dwarfs can fuse deuterium, a heavy form of hydrogen, but this process doesn't last long and doesn't produce much energy. The boundary between the largest planets and the smallest brown dwarfs is fuzzy and is still debated by astronomers. Some brown dwarfs are cool enough to have water vapor and even clouds in their atmospheres. The coolest brown dwarfs have temperatures similar to a hot oven. Exoplanets are planets that orbit stars other than our Sun. The first confirmed detection of an exoplanet around a Sun-like star was in 1995. Since then, over 5,000 exoplanets have been discovered. There are likely billions of planets in our galaxy alone. Many exoplanets are hot Jupiters, gas giants that orbit very close to their stars. These planets likely formed farther out and migrated inward. Some exoplanets orbit in the habitable zone of their stars, where conditions might be right for liquid water to exist on the surface. The habitable zone is sometimes called the Goldilocks zone because conditions are not too hot, not too cold, but just right for liquid water. Kepler 452b is one of the most Earth-like exoplanets discovered. It orbits a Sun-like star in the habitable zone and is only about 60% larger than Earth. The TRAPPIST-1 system contains 7 Earth-sized planets orbiting a small red dwarf star. 3 of these planets are in the habitable zone. Some exoplanets might be ocean worlds, completely covered in liquid water hundreds of kilometers deep. Other exoplanets might be lava worlds with surfaces hot enough to melt rock. Some might even have clouds made of vaporized rock or metal. Rogue planets are planets that don't orbit any star. They wander through space alone, ejected from their original star systems. There could be billions of rogue planets in our galaxy, possibly even more rogue planets than stars. Astronomers detect exoplanets using several methods. The transit method watches for a planet passing in front of its star, causing a tiny dip in brightness. The radial velocity method detects the wobble a planet causes in its star's motion. As a planet orbits, it tugs on its star, making the star move slightly. Direct imaging involves actually taking pictures of exoplanets, but this is difficult because planets are much fainter than their stars. Gravitational microlensing uses the gravity of a planet and its star to magnify the light from a more distant star. This can detect planets that would be impossible to find any other way. The atmospheres of some exoplanets have been analyzed by studying the starlight that passes through them. This has revealed the presence of water vapor, sodium, and other compounds. In the future, astronomers hope to detect biosignatures in exoplanet atmospheres, chemical signs that might indicate the presence of life. Stars form in giant clouds of gas and dust called nebulae. These clouds can be hundreds of light years across. The Orion Nebula is one of the closest star-forming regions to Earth, about 1,300 light years away. It's visible to the naked eye as a fuzzy patch in Orion's sword. When a region of a nebula becomes dense enough, gravity causes it to collapse and heat up, eventually forming a new star. As the cloud collapses, it spins faster, forming a disk of material around the forming star. Planets can later form from this disk. Young stars often produce powerful jets of material shooting out from their poles. These jets can be thousands of times longer than our solar system. Stars spend most of their lives fusing hydrogen into helium in their cores. This stage is called the main sequence, and it's the longest phase of a star's life. The more massive a star is, the shorter its life. A star 10 times more massive than the Sun might live only 20 million years, while a star half the Sun's mass could live 200 billion years. When a star like the Sun runs out of hydrogen in its core, it begins fusing hydrogen in a shell around the core. This causes the star to expand into a red giant. During the red giant phase, a star can become hundreds of times larger than it was on the main sequence. As a red giant, the Sun will likely engulf and destroy Mercury and Venus. Life on Earth would have ended long before this due to the increased heat. After the red giant phase, stars like the Sun shed their outer layers, creating beautiful structures called planetary nebula. The Ring Nebula is a famous planetary nebula visible in the constellation Lyra. It looks like a smoke ring in space. Planetary nebulae have nothing to do with planets. They were named by early astronomers who thought they looked like planets through their telescopes. The central star of a planetary nebula is the exposed core of the original star, now a white dwarf. This white dwarf slowly fades over billions of years. More massive stars, those with more than about 8 times the mass of the Sun, die in spectacular supernova explosions. A supernova can briefly outshine an entire galaxy of billions of stars. At its peak, a supernova can be as bright as the entire galaxy in which it resides. The closest supernova in recent history was in 1987, visible from the southern hemisphere. It occurred in a nearby dwarf galaxy called the Large Magellanic Cloud. Supernova 1987A was about 168,000 light-years away. This means the star actually exploded 168,000 years before we saw it. The Crab Nebula is the remnant of a supernova that was observed by Chinese astronomers in the year 1054. They described it as a guest star that was visible during the day. At the heart of the Crab Nebula is a pulsar spinning 30 times per second, the crushed core of the star that exploded. When massive stars explode, they can create neutron stars or black holes, depending on the mass of the core that remains. The most massive stars can become hypergiants, stars so large that if one replaced our Sun, it would extend past the orbit of Jupiter or even Saturn. VY Canis Majoris is one of the largest known stars. Its radius is about 1,500 times larger than the Sun's. If it replaced our Sun, it would extend almost to the orbit of Saturn. Eta Carinae is one of the most massive and luminous stars known. It's 100 times more massive than the Sun and 5 million times brighter. Eta Carinae is expected to explode as a supernova relatively soon in astronomical terms, possibly within the next 100,000 years. Some of the oldest stars in the universe are almost as old as the universe itself, over 13 billion years old. These ancient stars formed from almost pure hydrogen and helium because heavier elements hadn't been created yet by stellar nucleosynthesis. Population 3 stars are theoretical stars that formed from purely primordial gas with no heavy elements at all. None have been observed yet. Our Sun and most nearby stars are population 1 stars containing heavier elements created by previous generations of stars. Stars are basically giant balls of plasma held together by gravity and powered by nuclear fusion. The temperature and pressure in a star's core are so extreme that atomic nuclei can overcome their electromagnetic repulsion and fuse together. When 4 hydrogen nuclei fuse to create 1 helium nucleus, a tiny amount of mass is converted to energy according to Einstein's famous equation E = mc². This mass-to-energy conversion is what powers the Sun. About 4 million tons of matter is converted to pure energy every second in the Sun's core. The Sun produces about 386 billion megawatts of power. This is more energy than all of humanity has used throughout history. Only about 1/1000th of the Sun's energy actually hits Earth. Yet this is enough to power all weather, ocean currents, and life on our planet. Solar energy reaching Earth in just 1 hour is roughly equal to all the energy humanity uses in an entire year. Plants capture solar energy through photosynthesis, converting sunlight, water, and carbon dioxide into glucose and oxygen. This process powers nearly all life on Earth. All fossil fuels like coal, oil, and natural gas are ultimately stored solar energy. They form from ancient plants and organisms that captured sunlight millions of years ago. The sun will continue shining for about another 5 billion years before it runs out of hydrogen fuel in its core. Some galaxies are so far away that their light has been traveling through space for over 13 billion years before reaching us. When we look at distant galaxies, we're literally looking back in time. We see them as they were billions of years ago. The most distant galaxies we can see formed when the universe was less than 1 billion years old. They show us what the early universe was like. Galaxies come in several basic shapes. Spiral galaxies like the Milky Way, elliptical galaxies and irregular galaxies. Spiral galaxies have distinctive arms of stars, gas and dust spiraling out from a central bulge. Our Sun is located in one of the Milky Way's spiral arms. The Milky Way has several spiral arms, including the Perseus arm, the Sagittarius arm, and the Orion arm, where our Sun resides. Elliptical galaxies are smooth, featureless collections of stars ranging from nearly spherical to highly elongated shapes. They contain mostly old stars and little gas for new star formation. Irregular galaxies have chaotic structures with no particular shape. They're often the result of gravitational interactions with other galaxies. The large and small Magellanic Clouds are irregular dwarf galaxies that orbit the Milky Way. They're visible from the southern hemisphere as two fuzzy patches in the sky. When galaxies collide, the stars pass by each other, but the gas clouds collide and can trigger massive bursts of new star formation. The Milky Way and Andromeda galaxies are on a collision course. When they merge in about 4 billion years, they'll form a giant elliptical galaxy. Some astronomers have nicknamed the future merged galaxy Milkomeda, a combination of Milky Way and Andromeda. Galaxy clusters are groups of galaxies bound together by gravity. The Milky Way is part of a cluster called the Local Group. The Local Group contains about 50 galaxies, with the Milky Way and Andromeda being the two largest members. Beyond galaxy clusters are superclusters, enormous structures containing thousands of galaxies. The Local Group is part of the Virgo supercluster. The Virgo supercluster contains about 100 galaxy groups and clusters and spans about 110 million light-years. Even larger than superclusters are galaxy filaments and walls, vast structures that form the largest known patterns in the universe. Between these structures are enormous voids, regions of space with very few galaxies. These voids can be hundreds of millions of light-years across. The large-scale structure of the universe looks somewhat like a cosmic web or foam, with filaments and walls surrounding vast empty voids. This structure formed because of tiny density variations in the early universe that were amplified by gravity over billions of years. Dark matter plays a crucial role in the formation of cosmic structure. Its gravity pulls normal matter together to form galaxies and galaxy clusters. Dark matter makes up about 27% of the universe. We can't see it directly, but retry A continue can detect its gravitational effects on visible matter and light. Dark matter doesn't emit, absorb, or reflect light, which is why it's invisible to our telescopes. We only know it exists because of how it affects things we can see. Galaxies rotate in a way that suggests they contain much more mass than we can see. The visible stars alone don't provide enough gravity to hold galaxies together at their observed rotation speeds. Gravitational lensing provides another way to detect dark matter. Massive concentrations of dark matter bend light from more distant objects, creating distorted or multiple images. Scientists have proposed many candidates for what dark matter might be, including exotic particles called WIMPs, weakly interacting massive particles. Despite decades of searching, dark matter particles have not yet been directly detected in laboratory experiments. Some scientists think dark matter might be made of primordial black holes formed shortly after the Big Bang, though most evidence points to some type of exotic particle. Dark energy is even more mysterious than dark matter. It makes up about 68% of the universe. Dark energy appears to be causing the expansion of the universe to accelerate. Galaxies are moving away from each other faster and faster. Before dark energy was discovered, scientists expected the universe's expansion to be slowing down, due to the gravity of all the matter it contains. In 1998, observations of distant supernova showed that the universe's expansion is actually speeding up, not slowing down. The discovery of dark energy's accelerating effect earned the researchers the Nobel Prize in Physics in 2011. We don't know what dark energy is. It might be a property of space itself, or it might be a new type of energy field. Einstein's equations included a term called the cosmological constant that could act like dark energy. Einstein later called it his biggest blunder, but it might turn out to be correct after all. If dark energy continues to dominate the universe's expansion, galaxies outside our local group will eventually become unreachable, moving away faster than light can travel. In this scenario, the universe would become increasingly empty and dark, with galaxy clusters becoming isolated islands in an ever-expanding void. This possible future is sometimes called the Big Freeze or heat death, where the universe gradually runs down and becomes cold and dark. Another possibility is the Big Rip, where dark energy strengthens over time until it tears apart galaxies, then stars, then planets, and eventually even atoms. A third possibility is the Big Crunch, where the universe's expansion reverses and everything collapses back together, though current observations make this unlikely. The cosmic microwave background is radiation left over from when the universe was only 380,000 years old. Before this time, the universe was so hot and dense that atoms couldn't form. It was an opaque plasma of electrons and nuclei. When the universe cooled enough for atoms to form, light could suddenly travel freely through space. This light is what we detect as the cosmic microwave background. The cosmic microwave background has a temperature of about 2.7 degrees above absolute zero. It fills all of space uniformly. Tiny temperature variations in the cosmic microwave background, only about 1 part in 100,000, show us the density variations that would later grow into galaxies and galaxy clusters. The cosmic microwave background was predicted in the 1940s, but wasn't discovered until 1964 accidentally by 2 Bell Labs scientists. Arno Penzias and Robert Wilson were trying to eliminate noise from their antenna when they discovered the cosmic microwave background. They won the Nobel Prize for this discovery. The Wilkinson Microwave Anisotropy Probe and Planck satellites have mapped the cosmic microwave background in exquisite detail, giving us baby pictures of our universe. From studying the cosmic microwave background, we know the universe is flat, meaning it has no overall curvature on the largest scales. We also know the age of the universe to high precision, 13.8 billion years, give or take a few million years. The universe is expanding, but there's no center to this expansion. Every point in space is moving away from every other point. A helpful analogy is dots on the surface of an inflating balloon. As the balloon expands, every dot moves away from every other dot, but no dot is at the center. The expansion of space itself means that the most distant galaxies are moving away from us faster than the speed of light. This doesn't violate relativity because they're not moving through space faster than light. Space itself is expanding. The observable universe has a radius of about 46 billion light-years. This is larger than 13.8 billion light-years because of the expansion of space. The observable universe is just the part of the universe we can see. The entire universe might be much larger, possibly infinite. If the universe is infinite, it has always been infinite. The Big Bang happened everywhere at once. The first few 100 million years after the Big Bang are called the Dark Ages because no stars had formed yet. The universe was filled with neutral hydrogen gas. When the first stars formed and began shining, their ultraviolet light ionized the hydrogen gas around them. This period is called the epoch of ionization. The first stars were probably very massive, hundreds of times the mass of the Sun. They burned hot and bright, but died quickly in supernova explosions. These first supernovae spread the first heavy elements through space, seeding the universe with the building blocks needed for planets and life. Population 2 stars formed from gas enriched by the first generation of stars. They contain small amounts of heavy elements. The oldest population 2 stars we can observe are in globular clusters, spherical collections of hundreds of thousands of old stars orbiting our galaxy. Globular clusters orbit in a spherical halo around the Milky Way. They're among the oldest objects in our galaxy, over 10 billion years old. Open clusters are younger and smaller groups of stars that form together from the same gas cloud. The Pleiades is a famous open cluster visible to the naked eye. The Pleiades cluster contains several hundred stars and is only about 100 million years old, making it very young in astronomical terms. Stars in a cluster gradually drift apart over time due to gravitational interactions. Eventually, the cluster disperses and its stars become indistinguishable from other stars in the galaxy. Our Sun probably formed in an open cluster about 4.6 billion years ago. Its siblings from that birth cluster have long since scattered throughout the galaxy. Some astronomers are trying to identify the Sun's siblings by studying the orbits and compositions of nearby stars. A few candidates have been found, but none confirmed yet. The interstellar medium is the gas and dust between stars. It's extremely sparse by Earth standards, but contains the material from which new stars form. Interstellar space is not empty. On average, there's about 1 atom per cubic centimeter, though this varies widely from place to place. The interstellar medium contains mostly hydrogen and helium, with small amounts of heavier elements. About 1% is in the form of tiny dust grains. These dust grains block visible light but allow infrared light to pass through. This is why infrared telescopes can see into dusty regions where stars are forming. The pillars of creation in the Eagle Nebula are famous columns of gas and dust where new stars are forming. They're about 5 light-years tall. The Hubble Space Telescope took the iconic image of the pillars of creation in 1995. It's one of the most famous astronomical images ever taken. Infrared observations have shown dozens of young stars hidden inside the dusty pillars, invisible in optical light. Molecular clouds are dense regions of the interstellar medium where temperatures are low enough for molecules to form. These are the primary sites of star formation. The Taurus molecular cloud is one of the nearest star-forming regions, about 430 light-years away. It's producing mostly small, sun-like stars. Giant molecular clouds can be millions of times more massive than the Sun and hundreds of light-years across. They can give birth to thousands of stars. When a massive star dies in a supernova, the explosion can compress nearby gas clouds and trigger new star formation. This creates a cycle of stellar birth and death. Supernova remnants like the Cygnus loop show beautiful expanding shells of gas enriched with heavy elements from the exploded star. Some of the atoms in your body were created in the cores of ancient stars and dispersed by supernova explosions billions of years ago. Carl Sagan famously said, "We are made of star stuff." This is literally true. Every atom heavier than hydrogen in your body came from a star. The carbon in your cells, the calcium in your bones, the iron in your blood, all were forged in the nuclear furnaces of long-dead stars. Space is not a perfect vacuum. Even in the vast emptiness between galaxies, there are a few atoms per cubic meter. The temperature of empty intergalactic space is about 2.7 degrees Kelvin, the same temperature as the cosmic microwave background. Cosmic rays are high-energy particles, mostly protons, that zip through space at nearly the speed of light. They come from supernova explosions and other violent events. When cosmic rays hit Earth's atmosphere, they create showers of secondary particles. These cosmic ray showers are constantly raining down on us. Cosmic rays can damage electronics in spacecraft and pose a radiation hazard to astronauts on long missions, particularly missions beyond Earth's protective magnetic field. The Van Allen radiation belts are zones of intense radiation surrounding Earth, trapped by our planet's magnetic field. They were discovered by America's first satellite, Explorer 1. Solar storms can intensify the radiation belts and create beautiful auroras. They can also disrupt satellites and power grids on Earth. The largest recorded solar storm hit Earth in 1859. Known as the Carrington event, it caused auroras visible near the equator and disrupted telegraph systems worldwide. If a storm like the Carrington event happened today, it could cause widespread damage to satellites, power grids, and communication systems, potentially costing trillions of dollars. Space weather forecasting has become increasingly important as our technological infrastructure becomes more dependent on satellites and electrical grids. The Sun has an 11-year activity cycle. During solar maximum, sunspots and solar flares are common. During solar minimum, the Sun is quieter. The most recent solar minimum was around 2019 to 2020. Solar activity has been increasing since then toward the next maximum. Astronauts on the International Space Station orbit about 400 kilometers above Earth's surface. They experience 16 sunrises and sunsets every day. The International Space Station travels at about 28,000 kilometers per hour. It takes about 90 minutes to complete one orbit of Earth. Humans have continuously inhabited the International Space Station since November 2000. It's one of the most expensive structures ever built, costing over $100 billion. The ISS is about the size of a football field and weighs about 420 metric tons. It's the largest structure humans have ever built in space. Microgravity on the ISS causes many interesting effects. Flames burn as spheres instead of rising upward. Water forms floating spheres. Astronauts float unless they strap themselves down. Extended time in microgravity causes bone and muscle loss. Astronauts must exercise about 2 hours a day to maintain their health. Astronauts also experience fluid shifts in microgravity. Bodily fluids move toward the head, causing puffy faces and stuffy noses. This effect is sometimes called moon face. The human body gradually adapts to microgravity, but readjusting to Earth's gravity after a long mission can be challenging. Astronauts who've been in space for months may need assistance walking when they first return. The record for the longest single spaceflight is held by Valery Polyakov, who spent nearly 438 consecutive days aboard the Russian space station Mir. Yuri Gagarin became the first human in space on April 12, 1961. His spacecraft Vostok 1 completed one orbit of Earth in 108 minutes. Valentina Tereshkova became the first woman in space in 1963. She orbited Earth 48 times over almost 3 days. Neil Armstrong became the first human to walk on the moon on July 20, 1969. His famous words were, "That's one small step for man, one giant leap for mankind." 12 humans walked on the moon between 1969 and 1972 during the Apollo program. No one has returned since. The last people to walk on the moon were Eugene Cernan and Harrison Schmitt during Apollo 17 in December 1972. Footprints left on the moon by Apollo astronauts will remain for millions of years. Without wind or rain to erode them, they're essentially permanent. The Apollo astronauts left behind several rovers, scientific instruments, and American flags on the moon. However, the flags have likely been bleached white by decades of intense solar radiation. A total of 24 humans have traveled to the moon. Of these, 12 walked on its surface. The Soviet Union sent several robotic missions to the moon that successfully returned samples to Earth without human astronauts. China, India, Japan, and other countries have sent robotic missions to the moon in recent years, and several nations plan to send humans there in the coming decades. NASA's Artemis program aims to return humans to the moon and establish a sustainable presence there. The program plans to land the first woman and first person of color on the moon. Future lunar missions may establish a permanent base on the moon. Such a base could serve as a testing ground for technologies needed for Mars missions. The moon has ice in permanently shadowed craters near its poles. This ice could provide water for future lunar bases. Mars is the next major target for human space exploration. Several nations and private companies are working on plans to send humans to Mars. A human mission to Mars would take about 7 to 9 months each way with current technology. The total mission, including time on Mars, would likely last 2 to 3 years. Mars has about 1/3 of Earth's gravity. This is stronger than the moon's gravity, but still much weaker than what we're used to on Earth. The thin atmosphere on Mars provides some protection from cosmic rays, but not enough to protect humans from long-term radiation exposure. Future Mars habitats may need to be built underground or covered with Martian soil for protection. Mars has seasons similar to Earth because its axis is tilted at about the same angle as Earth's. However, Martian seasons are about twice as long because a Martian year is longer. Dust storms on Mars can cover the entire planet. The largest storms can last for months and reduce sunlight to a fraction of normal levels. Perseverance and other Mars rovers have been searching for signs of ancient life on Mars. While no definitive evidence has been found yet, the search continues. Mars once had liquid water on its surface. Dried-up river valleys and ancient lake beds provide clear evidence of a wetter past. Scientists think Mars may have been habitable billions of years ago when it had a thicker atmosphere and liquid water. If life ever existed there, it might have left fossils. Some meteorites found on Earth actually came from Mars. They were blasted off the Martian surface by asteroid impacts and eventually fell to Earth. One Martian meteorite, ALH 84001, contains structures that some scientists initially thought might be fossilized bacteria. This claim remains highly controversial. Venus is often overlooked as a destination for exploration because of its extreme conditions, but some scientists think floating stations in its upper atmosphere could be feasible. The upper atmosphere of Venus, about 50 kilometers above the surface, has temperatures and pressures similar to Earth's surface. Floating habitats could potentially exist there. Jupiter's moon Europa has a global ocean beneath its icy crust. This ocean might contain twice as much water as all of Earth's oceans combined. Europa's ocean is kept liquid by tidal heating from Jupiter's gravity. The constant flexing of Europa's interior generates heat through friction. Saturn's moon Enceladus also has a subsurface ocean. Geysers of water ice and organic compounds erupt from cracks in its south polar region. Both Europa and Enceladus are considered promising places to search for extraterrestrial life. Their subsurface oceans might provide habitable environments. Titan, Saturn's largest moon, has lakes and seas of liquid methane and ethane on its surface. It's the only other place in the solar system besides Earth with stable liquid on its surface. Titan has a thick atmosphere that creates weather patterns similar to Earth's water cycle, but with methane instead of water. The Cassini-Huygens mission dropped a probe onto Titan's surface in 2005. The probe survived for about 90 minutes, sending back images and data from the surface. Titan's surface temperature is about minus 179 degrees Celsius. At these temperatures, water ice is as hard as rock, and hydrocarbons can exist as liquids. Some scientists speculate that Titan could have exotic life based on liquid methane instead of liquid water. The concept of life as we don't know it is fascinating to scientists. Life elsewhere might be based on completely different chemistry than life on Earth. On Earth, all known life is carbon-based and requires liquid water. But perhaps life elsewhere could use silicon instead of carbon, or liquid methane or ammonia instead of water. The Drake equation is a famous formula that estimates the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. The equation includes factors like the rate of star formation, the fraction of stars with planets, and the fraction of planets that develop life. Different estimates for the Drake equation's factors lead to wildly different predictions, from humans being alone in the galaxy to millions of civilizations existing. The Fermi paradox asks, if intelligent life is common in the universe, where is everybody? Why haven't we detected any signs of other civilizations? Various solutions to the Fermi paradox have been proposed. Perhaps intelligent life is rare. Perhaps civilizations tend to destroy themselves. Perhaps we're looking in the wrong way or haven't looked long enough. SETI, the search for extraterrestrial intelligence, involves scanning the sky for radio signals or other signs of alien technology. SETI has been searching for decades without finding any confirmed signals. This could mean we're alone, or it could simply mean we haven't found the right frequency or looked in the right place yet. The WOW signal, detected in 1977, remains unexplained. It was a strong, narrow-band radio signal that lasted 72 seconds and has never been detected again. In recent years, fast radio bursts have been detected from distant galaxies. These are intense bursts of radio waves lasting only milliseconds. Most are thought to be natural phenomena, but their cause is still being studied. The Voyager 1 spacecraft is now in interstellar space, beyond the influence of the Sun's solar wind. It's the most distant human-made object. Voyager 1 was launched in 1977 and is now about 23 billion kilometers from Earth. Radio signals from Voyager take over 21 hours to reach Earth. Both Voyager spacecraft carry golden records containing sounds and images from Earth, intended as messages for any alien civilization that might find them. The golden records include greetings in 55 languages, music from various cultures, and sounds from Earth like whale songs and a mother's kiss. The Voyagers will continue traveling through space long after they run out of power. In tens of thousands of years, they'll pass near other star systems. New Horizons, which flew by Pluto, is also heading out of the solar system. It will eventually follow the Voyagers into interstellar space. The Pioneer spacecraft, which also carry plaques with information about Earth and humanity, preceded the Voyagers into deep space. All these spacecraft will likely outlast human civilization. They'll continue drifting through the galaxy for billions of years, silent ambassadors from Earth. In about 5 billion years, the Sun will begin its red giant phase. Earth will likely be destroyed, but these spacecraft will still exist, preserving a record of our existence. The ultimate fate of the universe remains uncertain. It depends on the nature of dark energy and how it evolves over time. In the far future, billions of years from now, most galaxies will have merged into giant elliptical galaxies. Star formation will gradually slow as gas is used up. Eventually, in trillions of years, the last stars will burn out. The universe will enter the black hole era, when black holes are the dominant objects. Black holes themselves will eventually evaporate through Hawking radiation, a quantum mechanical process. This will take unimaginably long, up to 10 to the 100 years for the largest black holes. After all black holes evaporate, the universe will consist only of a thin soup of fundamental particles spreading ever farther apart. This is the ultimate heat death of the universe. But all of this is incredibly far in the future. For now, the universe is young and full of light. Trillions of stars are still to be born. The story of the universe is also the story of matter becoming increasingly organized. From a nearly uniform hot plasma, gravity has sculpted galaxies, stars, planets, and on at least one planet, life. We are the universe becoming aware of itself. Through us, the cosmos contemplates its own existence. Every atom in your body has a cosmic history. The hydrogen in your body formed in the Big Bang. The oxygen you breathe was created in stars. The calcium in your bones came from supernova explosions. Looking up at the night sky connects you to the universe in a profound way. The light entering your eyes traveled for years, decades, or even millennia to reach you. When you look at a star, you see it not as it is now, but as it was when that light left on its journey to your eyes. The universe is vast beyond human comprehension. The distances between stars and galaxies are so immense that our minds struggle to grasp them. Yet despite this vastness, we can understand the universe through physics and mathematics. The same laws that govern falling apples on Earth also govern the motion of galaxies billions of light years away. Space exploration has given us new perspectives on our planet. The famous pale blue dot photograph taken by Voyager 1 from 6 billion kilometers away shows Earth as a tiny speck in a vast cosmic ocean. Carl Sagan reflected on this image, noting that everyone you've ever heard of, every human who ever lived out their lives on that pale blue dot suspended in a sunbeam. Earth is the only home we've ever known. In all the universe, we know of nowhere else that harbors life. This makes our planet precious and worth protecting. The universe is not only vast in space, but also in time. The universe has existed for nearly 14 billion years and may continue for trillions or even infinite years into the future. Human civilization is incredibly young compared to cosmic timescales. All of recorded history spans only about 5,000 years, a cosmic eye blink. Yet in that brief time, we've developed science and technology that allow us to understand our place in the cosmos. This is a remarkable achievement. The night sky has inspired humanity throughout history. Ancient cultures saw patterns in the stars and created myths to explain them. The constellations we recognize today are arbitrary patterns, but they've been passed down for thousands of years. Orion, Ursa Major, and Scorpius were recognized by ancient Greeks, Romans, Babylonians, and many other cultures. Different cultures saw different patterns in the same stars. The Big Dipper is part of Ursa Major Western cultures, but has been seen as a wagon, a plough, or different animals in other traditions. The ancient Polynesians used the stars for navigation, traveling thousands of kilometers across the open ocean, using only their knowledge of the sky. Ancient astronomers discovered that some stars wandered against the background of fixed stars. These wanderers were the planets, from the Greek word for wanderer. The geocentric model of Ptolemy placed Earth at the center of the universe. This model persisted for over 1,000 years despite its complexity. Nicolaus Copernicus proposed the heliocentric model, placing the Sun at the center of the solar system. This was simpler and more elegant than the geocentric model, but controversial at the time. Galileo Galilei was one of the first to use a telescope for astronomical observations. He discovered the moons of Jupiter, the phases of Venus, and craters on our moon. These observations supported the Copernican heliocentric model. They showed that not everything orbited Earth, and that celestial bodies were not perfect spheres. Isaac Newton developed the law of universal gravitation, showing that the same force that makes apples fall also keeps the moon in orbit and governs the motion of the planets. Newton's laws of motion and gravity were incredibly successful, accurately predicting planetary orbits and explaining a vast range of phenomena. Albert Einstein revolutionized our understanding of space, time, and gravity with his theories of special and general relativity. Special relativity showed that space and time are linked and that nothing can travel faster than light. Time actually passes more slowly for objects moving at high speeds. General relativity describes gravity not as a force, but as the curvature of space-time caused by mass and energy. Massive objects literally bend the fabric of space and time around them. Einstein's theories have been confirmed by countless experiments and observations. They're essential for understanding black holes, the expansion of the universe, and even for the operation of GPS satellites. Quantum mechanics, developed in the early 20th century, describes the behavior of matter and energy at the smallest scales. Quantum mechanics reveals that reality is fundamentally probabilistic at small scales. Particles don't have definite positions until they're measured. The double-slit experiment demonstrates the wave-particle duality of light and matter. Particles can behave like waves and exhibit interference patterns. Quantum entanglement is a phenomenon where particles become connected in such a way that measuring one instantly affects the other, regardless of the distance between them. Einstein called entanglement spooky action at a distance because he was uncomfortable with its implications. Yet experiments have confirmed that entanglement is real. Quantum mechanics and general relativity are both incredibly successful theories, but they're incompatible with each other. Combining them into a theory of quantum gravity is one of the biggest challenges in physics. String theory is one attempt to unify quantum mechanics and gravity. It proposes that fundamental particles are actually tiny vibrating strings of energy. String theory requires extra dimensions beyond the 3 spatial dimensions and 1 time dimension we experience. These extra dimensions might be curled up too small to detect. Loop quantum gravity is another approach to quantum gravity. It suggests that space itself is made of tiny discrete units like atoms of space. Whether string theory, loop quantum gravity, or some other approach is correct remains to be seen. Developing a complete theory of quantum gravity is an ongoing area of research. The universe continues to surprise us. Every answer we find leads to new questions. Every observation reveals new mysteries to explore. Dark matter and dark energy remind us how much we still don't understand. The majority of the universe consists of things we can't directly observe and don't fully comprehend. Yet this is what makes science exciting. There's always more to discover, always deeper mysteries to unravel. Future generations will explore places we can only imagine. They may walk on Mars, mine asteroids, establish colonies on other worlds. Perhaps someday humans or our descendants will travel to other star systems. Perhaps we'll find evidence of life elsewhere in the universe, or even make contact with other intelligent beings. Or perhaps we're alone, the universe's way of contemplating itself. Either possibility is profound. The cosmos is vast, ancient, and filled with wonders. From the quantum foam to superclusters of galaxies, from the first moments after the Big Bang to the far future, the universe tells an incredible story. And you are part of that story. You are made of atoms forged in stellar furnaces, organized by billions of years of evolution into a consciousness capable of understanding the cosmos. In these quiet moments before sleep, contemplate your connection to the universe. You are not separate from the cosmos, but intimately woven into its fabric. The same energy that powers stars flows through you. The same atoms that make up distant galaxies make up your body. You are, quite literally, the universe experiencing itself. Rest now, under the same stars that shone on your ancestors and will shine on your descendants. Float in the cosmic ocean, a small but precious part of something infinitely vast and beautiful. The universe continues its ancient dance. Galaxies spin, stars are born and die, planets orbit in the darkness. And here you are, a conscious being contemplating it all. What a privilege it is to exist in this remarkable universe. What a gift to be aware, to wonder, to understand even a fraction of cosmic mysteries. As you drift towards sleep, let these thoughts of the cosmos comfort you. You are home in the universe. This is where you belong. The stars shine on in the darkness, the universe expands, time flows forward, and you are part of it all, now and always. Rest well, cosmic being. Dream of stars and galaxies, of nebulae and black holes, of the infinite mysteries that await discovery. The universe is patient. It has waited billions of years. It will continue long after we're gone. But for this moment, you are here, aware, alive under these stars. And that is enough. That is everything. Good night. Retry, continue. The void between stars is not truly empty. Quantum fluctuations cause particles to spontaneously appear and disappear, creating a seething foam of energy at the smallest scales. Virtual particles pop into existence in pairs, matter and antimatter, and annihilate each other almost instantly. This happens everywhere, all the time, even in the emptiest regions of space. Near the event horizon of a black hole, these virtual particle pairs can be separated. One falls into the black hole while the other escapes as real radiation. This is Hawking radiation. Through this process, black holes very slowly lose mass and energy. The smaller a black hole gets, the faster it radiates. In the final moments before evaporation, a black hole releases a burst of energy. A black hole the mass of our Sun would take 10 to the 67 years to evaporate through Hawking radiation. This is far longer than the current age of the universe. The temperature of Hawking radiation from a stellar mass black hole is incredibly low, far colder than the cosmic microwave background. These black holes are actually absorbing more energy than they emit right now. Only in the far future, when the universe has expanded and cooled enough, will black holes begin to lose mass faster than they gain it from their surroundings. Primordial black holes, if they exist and are small enough, could be evaporating right now. A primordial black hole, the mass of a mountain, would take about the age of the universe to evaporate. The final explosion of an evaporating black hole would release as much energy as millions of nuclear bombs, though this would be spread across many forms of radiation. Information appears to be lost when matter falls into a black hole, which contradicts the principles of quantum mechanics. This is known as the black hole information paradox. Stephen Hawking proposed that information might be preserved in the Hawking radiation, encoded in subtle correlations too complex to detect in practice. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary, like a hologram. This might help resolve the information paradox. According to the holographic principle, our three-dimensional universe might be like a projection from information stored on a two-dimensional cosmic horizon. These ideas push the boundaries of our understanding. They suggest reality might be far stranger than our everyday experience suggests. Time itself might not be fundamental. Some theories suggest time emerges from more basic quantum processes, like temperature emerges from the motion of atoms. If time is not fundamental, the flow of time we experience might be an illusion, a result of the particular way our brains process information. Yet this doesn't make time any less real to us. Our experience of time, our memories and anticipation, are fundamental to our consciousness and existence. The arrow of time, the fact that time flows in one direction, is connected to entropy. The second law of thermodynamics states that entropy always increases. Entropy is a measure of disorder. The universe began in a highly ordered state and has been becoming more disordered ever since. This gives time its direction. We remember the past, but not the future, because our memories are records formed by entropy increasing processes. The physical basis of memory requires the arrow of time. The low entropy state of the early universe is something of a mystery. Why did the universe begin in such an ordered state? This initial condition made all subsequent structure possible. Without the universe starting in a low entropy state, stars, planets, and life could never have formed. The arrow of time and the possibility of complexity are intimately linked. Some scientists speculate that our universe might be part of an eternally inflating multiverse where different regions have different physical laws. In this scenario, our observable universe is just one bubble in an infinite cosmic foam, with new universes constantly being created through eternal inflation. Each bubble universe might have different values for fundamental constants. The strength of gravity, the mass of electrons, the cosmological constant might all vary. Most bubble universes would be sterile, incapable of supporting life. We find ourselves in one that can support life because, obviously, we couldn't exist in one that couldn't. This is an example of the anthropic principle. Some properties of the universe appear fine-tuned for life because if they were different, we wouldn't be here to observe them. Whether the multiverse hypothesis is true science or unfalsifiable speculation is debated by physicists and philosophers. Some argue that if we can never observe other universes, the multiverse isn't science. Others counter that it's a natural consequence of well-established theories like inflation. The debate touches on deep questions about the nature of scientific explanation and what we should expect from our theories. Perhaps someday we'll find evidence in the cosmic microwave background of collisions with other bubble universes. Such evidence would be remarkable confirmation of the multiverse hypothesis. Or perhaps we'll develop a deeper theory that explains why physical constants have the values they do, removing the need for anthropic reasoning. Science progresses through such uncertainties. What seems mysterious today may become clear tomorrow, though new mysteries will surely take their place. The history of science shows us repeatedly that reality is stranger than we imagine. From atoms to black holes to quantum mechanics, nature defies our intuitions. Yet nature is also comprehensible. The human mind, evolved to survive on the African savanna, can understand quantum mechanics and general relativity. This is remarkable. Mathematics is the language we use to describe the universe. Equations capture relationships between physical quantities with precision and elegance. The unreasonable effectiveness of mathematics in describing nature is something of a mystery. Why should abstract mathematical structures correspond so well to physical reality? Perhaps mathematics is effective because the universe is fundamentally mathematical. Or perhaps our brains evolved to recognize patterns, and mathematics is our highest expression of pattern recognition. Some physicists believe we may someday find a theory of everything, a single equation that describes all fundamental forces and particles. Such a theory would unify quantum mechanics and general relativity, explaining everything from the smallest particles to the largest cosmic structures. But even a theory of everything wouldn't answer all questions. It couldn't tell us why that particular theory describes our universe or why anything exists at all. The question of why there is something rather than nothing may be unanswerable by science. It touches on philosophy and metaphysics as much as physics. Some philosophers argue that nothingness is actually unstable and something must exist. Others suggest the question is meaningless because nothing cannot be consistently defined. These deep questions have no easy answers. They remind us of the limits of human knowledge and the profound mysteries that remain. Yet the fact that we can ask such questions is itself remarkable. Consciousness arising from matter organized in particular ways can ponder its own existence. Your brain contains about 86 billion neurons, each connected to thousands of others. These connections form networks of incredible complexity. The patterns of electrical and chemical signals flowing through these networks somehow give rise to your thoughts, feelings, memories, and sense of self. How consciousness arises from neural activity is one of the deepest mysteries in science. We know a lot about the brain, but we don't fully understand how it produces subjective experience. This is sometimes called the hard problem of consciousness. Why does information processing in the brain feel like something? Why is there an inner experience? Some philosophers argue consciousness is fundamental, not reducible to physics. Others believe it will eventually be explained in purely physical terms. Consciousness might not be unique to humans or even to Earth. If the conditions that give rise to consciousness are common, awareness might be widespread in the universe. Perhaps consciousness requires only information processing of sufficient complexity. In that case, artificial intelligence might become conscious, as might alien minds very different from our own. Or perhaps consciousness requires something specific about biological neural networks. We don't yet know. The possibility of alien consciousness raises fascinating questions. How would minds that evolved under different conditions perceive reality? Would aliens with different sensory organs see the universe differently than we do? Would their mathematics be the same as ours? Most scientists believe that mathematics and fundamental physics would be universal. Any technological civilization would discover the same mathematical truths and physical laws. But the way they conceptualize and express these ideas might be very different. Their art, music, and philosophy would surely be alien to us. Making contact with an alien civilization would be the most profound discovery in human history. It would show we're not alone and offer new perspectives on existence. But the vast distances between stars make contact difficult. Even if intelligent life is common, civilizations might be too far apart to ever communicate. A radio signal to the nearest star system takes over 4 years to arrive. A conversation with aliens there would have 8 years between question and answer. For more distant civilizations, communication delays would be decades, centuries, or millennia. Real-time conversation would be impossible. Despite these challenges, the search for extraterrestrial intelligence continues. SETI listens for signals, while other projects look for technosignatures, signs of alien technology. Some scientists propose sending our own messages to the stars, though this is controversial. Should we announce our presence, not knowing what might be out there? The universe might be teeming with life, or life might be rare. We might be surrounded by civilizations, or we might be alone. We don't yet know. What we do know is that the universe is vast and ancient. It has had billions of years and trillions of potential sites for life to develop. Earth formed about 4.6 billion years ago from the debris surrounding our young sun. At first, it was a molten ball of rock. Early Earth was bombarded by asteroids and comets. These impacts brought water and organic compounds, the building blocks of life. The moon's formation from a giant impact likely caused Earth's crust to melt. The planet had to cool before oceans could form and remain stable. The earliest evidence of life on Earth dates back about 3.7 billion years, just a few 100 million years after the planet's surface cooled enough for liquid water. Life arose surprisingly quickly once conditions allowed. This suggests that the origin of life might be relatively easy given the right conditions. Or we might be incredibly lucky. With a sample size of 1, we can't know how probable life is. This is one reason finding life elsewhere would be so significant. Early life on Earth was microscopic and simple. For billions of years, life consisted only of single-celled organisms. These early microbes transformed Earth's atmosphere. Photosynthetic bacteria began producing oxygen as a waste product about 2.4 billion years ago. The Great Oxidation Event was catastrophic for life that couldn't tolerate oxygen. But it made possible the evolution of complex life that uses oxygen for energy. Eukaryotic cells with nuclei and complex internal structures evolved about 2 billion years ago. This was a crucial step toward complexity. Multicellular life appeared much later, perhaps around 600 million years ago. Before then, all life was single-celled. The Cambrian explosion, about 540 million years ago, saw a rapid diversification of life forms. Most major animal body plans appeared in a relatively short time. Life has survived multiple mass extinctions. The largest, the Permian-Triassic extinction, killed about 96% of marine species and 70% of land species. Life recovered from this catastrophe, though it took millions of years. Evolution continued, producing new forms to fill empty ecological niches. The dinosaurs dominated for about 165 million years before their extinction. Their reign was much longer than mammals have dominated so far. Mammals had existed alongside dinosaurs for over 100 million years, but remained small and mostly nocturnal. The dinosaur extinction gave mammals their opportunity. Primates evolved about 55 million years ago. The lineage leading to humans split from other apes about 6 to 7 million years ago. Anatomically, modern humans appeared in Africa about 300,000 years ago. For most of that time, we were hunter-gatherers living in small groups. Agriculture was invented only about 10,000 years ago. This allowed permanent settlements and eventually cities, civilization and technology. Written history covers only the last 5,000 years or so. Everything before that is prehistory, reconstructed from archaeological evidence. All of recorded history is just a tiny fraction of human existence, which is itself a tiny fraction of life's history, which is a tiny fraction of Earth's age, which is a tiny fraction of the universe's age. We exist at one particular moment in cosmic history. The universe is middle-aged, with many billions of years of star formation still ahead. Future intelligent beings, whether our descendants or others, might look back on our era as ancient history, the way we view early civilizations. Or perhaps no one will be there to look back. The future is unwritten. Humanity's long-term fate depends on choices we make and forces beyond our control. We're the first species on Earth capable of understanding our cosmic context. We know we live on a planet orbiting a star in a galaxy among billions. We know the universe had a beginning and will have an end. We know we're made of atoms forged in stars. We know we're connected to everything that exists. This knowledge brings with it responsibility. We're the stewards of Earth's biosphere, at least for now. The decisions we make affect countless other species. We're also the first species capable of leaving our home planet. We've sent probes to every planet in the solar system and landed humans on the moon. In the near future, we may establish permanent settlements on the moon and Mars. Further in the future, we might spread throughout the solar system. Perhaps eventually, we'll develop the technology to travel to other stars. Generation ships carrying thousands of people might journey for centuries or millennia to reach new worlds. Or perhaps we'll never leave our solar system. The distances between stars may prove insurmountable for biological beings like us. Advanced civilizations might send robot probes or even transmit information to construct themselves at distant locations. Intelligence might spread even if bodies cannot. The far future is impossible to predict. Technology advances in unexpected directions. What seems impossible today may be routine tomorrow. A person from just a century ago would find our world unrecognizable. Smartphones, the internet, space stations, genetic engineering would all seem like magic. What will the world look like a century from now? 1,000 years from now? 1,000,000 years from now? We cannot know, but we can know that we're part of a cosmic story stretching from the Big Bang to the far future. We're links in a chain of causation billions of years long. Every event in your life, from your first breath to this moment, has a history extending back to the origin of the universe. The atoms in your body were created in stellar furnaces. They were part of the molecular clouds that formed our solar system. They were in the disk of debris that coalesced into Earth. They cycled through ancient oceans and rocks over billions of years. They were part of the air breathed by dinosaurs, part of ancient trees, part of countless organisms throughout Earth's history. Now they're part of you. After you, they'll become part of other things, cycling through Earth's systems for billions of years to come. Eventually, in about 5 billion years, the sun will expand into a red giant. Earth will be scorched or consumed. Any atoms that escape Earth's destruction will be dispersed when the sun its outer layers, not returning to the interstellar medium. These atoms might someday become part of new stars, new planets, perhaps new life. The cycle continues on timescales we can barely comprehend. Hydrogen atoms are nearly eternal. A hydrogen atom in your body might be 13 billion years old, formed in the first few minutes after the Big Bang. This atom has been part of countless stars, planets, and perhaps countless living beings across cosmic history. Its journey spans almost the entire age of the universe, and now it's part of you, helping carry out the biochemical processes that sustain your life and consciousness. Every breath you take contains atoms that were once part of Julius Caesar, Cleopatra, Leonardo da Vinci. We're all literally connected through the atoms we share. The oxygen you're breathing right now was produced by plants and photosynthetic bacteria. You're inhaling the waste product of countless organisms. When you exhale carbon dioxide, you're feeding plants. This symbiosis between oxygen producers and oxygen consumers has existed for billions of years. Life on Earth is deeply interconnected. Ecosystems form webs where every species depends on many others. We're part of these webs, not separate from them. The biosphere itself might be considered a single system, with all life interacting to regulate Earth's atmosphere and environment. This is the Gaia hypothesis. Whether Gaia is literally true or merely a useful metaphor, it reminds us that Earth's environment is shaped by life, and life is shaped by the environment. The Amazon rainforest produces much of its own rainfall through transpiration. The forest creates the conditions it needs to survive. Coral reefs create complex three-dimensional structures that provide habitat for thousands of species. The reef is built by the organisms it supports. These examples show how life actively shapes its environment. We're not passive inhabitants, but active participants in Earth's systems. Human activity now shapes Earth's climate and ecosystems on a global scale. The consequences of our actions ripple through the entire biosphere. We're living through the Anthropocene, a proposed epoch defined by humanity's significant impact on Earth's geology and ecosystems. Future geologists might mark our era by plastic in rock layers, by shifts in isotope ratios from fossil fuel burning, by mass extinctions. We have the power to destroy or to preserve, to harm or to protect. The choice is ours. Looking at Earth from space shows no borders, no nations, just one fragile blue sphere surrounded by the vastness of space. From the Moon, Earth is a colourful oasis in the black void. From Saturn, as captured by Cassini, Earth is a pale blue dot barely visible against the rings. These views remind us that we share one small planet. Our divisions seem petty when viewed against the cosmic backdrop. We're all crew members on spaceship Earth, travelling through the cosmos together at about 500 kilometers per second. That's how fast our solar system orbits the center of the Milky Way. We're on a cosmic journey, whether we realize it or not. The center of the Milky Way lies in the direction of the constellation Sagittarius. That's where Sagittarius A star, our galaxy's supermassive black hole, resides. Looking toward Sagittarius, we're looking toward the heart of our galaxy, though dust obscures the view in visible light. Looking away from Sagittarius, we see toward the outer reaches of the galaxy and beyond, where other galaxies fill the deep universe. The Andromeda Galaxy is visible to the naked eye on clear, dark nights. It appears as a faint smudge, but that smudge is a trillion stars 2.5 million light-years away. The light you see from Andromeda left those stars 2.5 million years ago, when early human ancestors were just beginning to walk upright. Every distant galaxy you observe is a time machine showing you the past. The farther away it is, the farther back in time you see. The most distant galaxies visible to our best telescopes show us the universe as it was over 13 billion years ago, less than a billion years after the Big Bang. These ancient galaxies are different from modern ones. They're smaller, more irregular, actively forming stars at prodigious rates. Many have merged with other galaxies over cosmic time. The Milky Way itself has absorbed dozens of smaller galaxies throughout its history. Evidence of these ancient mergers remains in streams of stars orbiting our galaxy, the remnants of galaxies torn apart by the Milky Way's gravity. Some stars in our galaxy are older than the Milky Way itself, remnants of smaller galaxies that merged to form ours. The universe has a complex history of creation and destruction, building and merging, on all scales from atoms to galaxies. Nothing is permanent. Stars are born and die. Galaxies merge and evolve. Even black holes eventually evaporate. Yet nothing is truly destroyed. Energy and information are conserved, even as they transform into different forms. The atoms in your body will persist long after you're gone, becoming part of other things, continuing their ancient journey through the cosmos. This is both humbling and comforting. We're temporary, but we're part of something permanent. We're individual, but we're part of a greater whole. Your consciousness is a temporary pattern in the matter and energy of the universe, a pattern that can think and feel and wonder. For a brief time, the universe experiences itself through you. Your awareness is the universe's awareness. Your wonder is the cosmos contemplating itself. This moment of consciousness is precious. It's the universe's gift to itself, a chance to see and understand. When you look at a star, photons that traveled for years through empty space end their journey in your eyes. That light becomes electrical signals in your brain. Through an incomprehensible process, those signals become conscious experience. You perceive the star, feel wonder, understand what you're seeing. This is the magic of consciousness, the mystery at the heart of existence. Matter arranged just so becomes aware. And what do we do with this awareness? We marvel, we question, we seek to understand. Human curiosity has taken us from wondering at the stars to walking on another world, from crude telescopes to space stations. We've deciphered the genetic code, split the atom, discovered quantum mechanics, general relativity, the Big Bang. Each generation builds on the knowledge of those before, standing on the shoulders of giants, seeing farther and deeper. What future generations will discover, we can only imagine. They'll look back on our era, on our understanding, and see how far they've come. But they'll also be grateful to us, as we are grateful to those who came before, for the questions we asked and the answers we found. Every question answered reveals new questions. Every mystery solved unveils deeper mysteries. This is the endless adventure of science. The universe seems designed to be interesting. Wherever we look, we find complexity, beauty, phenomena that inspire wonder. From the quantum foam to the cosmic web, from the elegance of E equals mc squared to the complexity of DNA, nature astounds us. Perhaps we find nature beautiful because we evolved in it. Our aesthetic sense might be shaped by exposure to natural patterns and structures. Or perhaps there's something objectively beautiful about mathematical elegance, symmetry, and the deep unity underlying diverse phenomena. The fact that simple equations describe such complexity is remarkable. The Schrödinger equation governs quantum mechanics. Einstein's field equations describe gravity. These equations are compact enough to write on a t-shirt, yet they contain within them the behavior of stars, atoms, space, and time. This compressibility of nature, its describability by simple rules, is what makes science possible. Without it, we could never understand anything. The universe didn't have to be understandable. It could have been chaos. But instead, it follows rules, and those rules can be discovered. This is perhaps the deepest mystery of all. Why is there order rather than chaos? Why can the universe be understood? These questions may have no answer, or the answer might be beyond our capacity to comprehend. But we can still ask, still wonder. And in the wondering, in the questioning, we fulfill something essential to human nature. We reach beyond ourselves toward understanding. The ancient philosophers looked at the stars and wondered. We're their descendants, still looking up, still wondering, with tools they could never have imagined. But the sense of wonder remains the same. The stars still inspire the same questions they always have. Who are we? Where did we come from? Where are we going? Science provides some answers, but raises new questions. The more we learn, the more we realize how much we don't know. The boundary of knowledge is not a wall, but a horizon. As we approach it, it recedes, revealing ever more territory to explore. This journey has no end. There will always be more to discover, deeper understanding to seek, further mysteries to unravel. And that's as it should be. A universe fully understood would lose its magic. Mystery and wonder are gifts. So rest now in the knowledge that you're part of something vast and mysterious. You're a conscious pattern in the cosmic tapestry. The universe flows through you and around you. You're made of stardust, animated by nuclear fusion, aware through incomprehensible complexity. You are the cosmos experiencing itself. You are the universe wondering at its own existence. You are stardust contemplating the stars. Sleep peacefully, knowing you belong here. The same forces that shaped galaxies shaped you. The same laws that govern stars govern your atoms. You're home in this universe. There's nowhere else you could be. This is where you've always been, since the atoms of your body formed in ancient stars. Dream of the infinite. Dream of stars and space and time. Dream of the great cosmic dance that includes everything that exists. The universe continues while you rest. Planets orbit, stars shine, galaxies turn, and you are part of it all. Good night, child of the cosmos. Rest under the light of ancient suns. Sleep beneath the same sky that has witnessed the entire history of the universe. You are precious, a brief flowering of consciousness in an ancient cosmos. Cherish this gift of awareness, this moment of existence. The stars shine for you, the universe exists for this moment of wonder, and you exist to experience it. Sleep now and dream of infinity.